I'm Kevin Shen. You've seen me in such fine quality, epic chemistry videos like equilibrium and equilibrium 2. Is there a connection? And K is products over reactants? Part 4. Okay, this is the last section of chapter 13. Okay, and we've been talking about equilibrium. We have gone through a number of problems looking at K, our equilibrium constant, at different values. So we're looking here at the mid-range Ks for this. I am not going to be solving problems here simply because of the timing that's involved, and it also uses the quadratic formula, which is highly unlikely they're going to be using that on the AP exam. Really highly unlikely. Okay? So when we look at something like this, no simplification. We'll choose x to be small, but we don't get to simplify it. So we're going to have to use the quadratic formula to solve for that. And this is the problem here. Again, like I said, I'm not going to work the problem with you guys. I am going to link you to an equilibrium problem that does use the quadratic. So you can go ahead and figure that one out. Okay, if you're using pressure, for example, it's the same idea. You're going to use the quadratic formula, except you're going to be working with pressures this time around. And we're only working with pressure, so we're not working with concentration. Okay, again, I'm linking you to that how to solve equilibrium problems using the quadratic. But I did want to get through this last part here, and that's Le Chatelier's principle. We've talked about it before. If a stress is applied to a system at equilibrium, the position of the equilibrium is going to shift to reduce the stress. Okay? So when we look at something like this here, for example, I have H2 plus, oh, there's the I2 down here. So I have here H2 plus I2, and notice how this is going back and forth, and we get 2HI. All right, so this is at equilibrium. If we have too much reactant, okay, that puts a lot of weight in this. Remember, this is equilibrium. If we have too much reactant, which way will the reaction shift to reset the equilibrium? Is it going to shift to the left, where we're making more reactant? That doesn't seem to be the right answer. Or are we going to shift to the right, speed up the process of making more product to set it up at equilibrium? Okay, so the idea is this: if there's too much reactant, then the speed at which products are made is going to go faster to bring it back up. This is equilibrium. Too much material, more product has to be made in order to stabilize it, to go back to it. Same thing if you do the other side. If you have too much product, what do? It's going to shift to the left to make more reactant, thus stabilizing, relieving the stress. So when you're talking about relieving the stress, guys, it's either the reaction's either going to shift to the left to make more reactant, or it's going to shift to the right to make more product. That's the idea behind the thing. But with Le Chatelier, you have three kinds of stress: the amount of material, pressure, and temperature. So if you're adding products, that makes Q greater than K. So it's going to shift to the left. Okay, if you're removing reactant, makes Q bigger than K. Okay, if you're removing the reactant, that also means it's going to shift to the left. Okay, if you're adding reactant, makes the Q less than K, it's going to shift to the right. So look at the direction where the Q, if it's greater than K or less than K, because remember, if Q, which is our equilibrium right now, at this moment, if we compare it to A, our equilibrium constant, if it's the same, then the system's at equilibrium. But if Q is greater than K, then what happens is it must shift to the left to make more reactant. Less product, more reactant. If we remove reactant, okay, then what's happening, you are creating an imbalance, and then the system is going to shift to the left again. to make more reactant, to make up for what was removed. Okay? If we add extra reactant, okay, then what happens is you have too much reactant, not enough product. It's going to shift to the right to make more product. If we remove product, again, we make the Q less than K, then guess what? That means it's going to shift to the right to make more product, to make up for what was removed. Okay? So again, determining the effect on Q is going to tell you the direction of the shift. Now, what about when we're changing pressure? How in the world do we change the pressure? Easy, changing the volume. Okay? The system is going to move in the direction that has the least number of moles of gas. Okay? Why is this happening? Because partial pressures and concentrations change. A new equilibrium has to be reached. So what's the system trying to do? It's trying to minimize the number of moles of gas that's in there. Okay? Now, change of pressure. Another way we could do it is adding an inert gas or a noble gas. Gases that don't really react, like xenon, helium, neon, argon, etc. So what happens is the partial pressures of the reactants and products are not changed. There's no effect on the equilibrium position on this. It's not going to make a difference for that. When you are adding the noble gas, the inert gas, the gas that doesn't react at all, it doesn't change things. So how in the world do we change the pressure? If we change the volume, and if you change the volume, then again, you're looking at the smallest number of moles of gas that's there. Okay? Let's move on. Change in temperature as we wind down chapter 13. It affects the rates of both the forward and the reverse reactions. Stop and think about it. If you're adding heat to something, you're going to make the atoms and the molecules move faster. They are much more likely to go and collide with each other. Stop and think about that. Okay? So, if it's an exothermic reaction, it's going to shift to the left where delta H is less than 0. Remember, delta H is our enthalpy, total energy content in the system. That's enthalpy. It's less than 0. It's negative. We would expect it to shift to the left. When it's endothermic, it's going to shift to the right. Where our delta H is greater than 0, our delta H, our enthalpy, total energy content of the system. If it's a positive number, it tells you it's endothermic. Remember, endothermic, you're absorbing energy, you're absorbing heat energy, whereas exothermic, you're giving off the heat energy. Okay? So, with that, ladies and gentlemen, we are done with chapter 13. I'm going to link you, like I said, I will link you guys for the videos. I am going to see about having you guys do a little something with Le Chatelier's principle as we move on to the next thing. Okay? All right, this is Kevin Shen signing off. All hail the Imperial Guard!